faithfully delivering value, interpreting great books from around the world. Hello, this is Sally's Book Club. Today, the book we're going to interpret is The History of Human Navigation. If you were going to an unfamiliar place, how would you plan your route? Exactly. Just open the map up on your phone, search for the destination, and the most convenient route pops up. Before the internet and mobile phones became common, families had to keep a city transit map at home, then study it with a magnifier to find nearby buses. Even so, sometimes you still ended up taking wrong turns. But did you know the emergence of modern maps marks a huge achievement in humanity's quest for direction? This book chronicles humanity's navigation efforts from ancient times to today. Its subtitle is From Compass to GPS, The Past and Future of Navigation and Positioning. The author is Hiawatha Bray, a veteran tech journalist named among America's top 10 most influential tech reporters by Computer Marketing Magazine. Next, I'll explore this book through 4 chronological questions. First, how did humans navigate before the 20th century? Second, how did radio enable navigation and positioning? Third, how did the GPS global positioning system develop? Fourth, how do digital maps impact our lives today? First, let's dive into part 1, how humans navigated before the 20th century. The sun, moon, and stars were crucial directional guides for ancients. As early as 3000 BC, Egyptian scholars used celestial bodies for precise navigation. Through naked eye observation, they refined 36 constellation star charts and recorded their movements. Later, astronomers identified Ursa Major and Ursa Minor, constellations always visible above the horizon. Polaris, North Star in Ursa Minor, showed true north to ancient navigators. Sailors used Polaris with basic trigonometry to measure their approximate distance from the equator. This distance is latitude. One fascinating method involved tying a string to a tooth, pointing it at Polaris. The string ground angle revealed their latitude. Of course, having only latitude isn't enough for precise navigation. In the 2nd century BC, the ancient Greek mathematician Hipparchus proposed that maps should consist of parallel east-west latitude lines and north-south longitude lines converging at the poles. About 300 years later, based on this idea, the ancient Roman astronomer Ptolemy completed his 8-volume masterpiece, Geography, which included a series of world and regional maps that had a profound impact on later generations, known as Ptolemaic maps. To create these maps, Ptolemy collected longitude and latitude coordinates for over 8,000 places from sailors and travelers. Although they weren't perfect and had many errors, Ptolemaic maps pioneered scientific mapmaking. Now that we've covered maps, let's talk about another very important navigation tool. The earliest documented compass appeared in 1044 AD in northern Song literature, Wujing Zanyao, which mentioned a floating south-pointing fish, a thin fish-shaped magnet floating on water with its head pointing south and tail north. By the 12th century, the compass was already used in maritime navigation. The invention of the compass allowed sailors to no longer rely solely on celestial bodies and landmarks for direction, greatly reducing the risks of long voyages. As geographical theory and navigation technology matured, cartographers began to shine. In the late 17th century, Italian geographer Cassini and his descendants, with the support of King Louis XIV of France, spent over a century completing precise mapping of the entire country. Starting in the 18th century, people began scientifically advancing global mapping. For example, navigator Captain Cook mapped New Zealand and Australia's east coast. Gradually, humanity depicted the true appearance of the world. After millennia of developing navigation from scratch, human navigation and positioning technology advanced rapidly in the 20th century, with the most important invention being radio. In part 2, we'll discuss how radio technology developed and how it served navigation and other fields. In the late 19th century, Italian inventor Marconi invented radio. After continuous trials and improvements, by 1895, he could send telegraphs several kilometers away, and researchers soon realized radio could also be an excellent navigation tool. Because radio waves from a fixed point travel in straight lines, if you can pinpoint the signal direction, you can follow it home. In 1902, American engineer and inventor John Stone received a patent for a radio direction finding device. In 1914, World War I broke out, the first conflict where aircraft played a dominant role. But getting planes to accurately locate targets and return safely was difficult, especially at night or in bad weather. That's where radio navigation came into play. Initially, radio transmitters were carried on planes. Ground crews would receive pilots' signals, calculate positions, then relay them back. Early radio equipment was bulky, adding significant weight to planes, and the back-and-forth communication reduced positioning, timeliness, and accuracy. Later, Germans developed a new land-based radio transmission method. The method involved ground-based radio stations, with navigators using special watches on board to receive signals. By receiving signals from two stations and finding their intersection point, they could determine the plane's location. This improved positioning accuracy and being passive signal reception didn't easily reveal their position. After WWI, global aviation rapidly expanded, inspired by land-based radio tech. In 1920, the U.S. Commerce Department developed the four-course radio range, where stations simultaneously transmitted overlapping signals. If pilots heard equally strong signals, they were on the beam between two stations. Unequal strengths meant off-course, requiring directional adjustment. Simultaneously strengthening signals indicated approaching the stations. Conversely, weakening meant veering off course. While planes had navigation solved, what about long-haul ships? On August 3, 1958, the U.S. Navy's nuclear submarine Nautilus reached the North Pole, the first vessel ever to do so. Consider, underwater there are no stars for navigation. Radio signals can't penetrate, and near poles, compasses become unreliable. So how did they actually achieve this? The answer is the gyroscope. Newton's law of inertia tells us that without external force, an object maintains its motion state. French physicist Foucault created a device based on this principle called the gyroscope. Without external force, the gyroscope's axis always points to the same direction, anywhere on Earth. Thus, gyroscopes gradually became vital navigation aids, later joined by accelerometers. Also based on Newtonian physics, accelerometers detect acceleration or deceleration, calculating position over time. Combined with gyroscope orientation, they determine position relative to starting point. This system, inertial navigation, enables missiles and planes to fly autonomously without external signals, significantly improving accuracy despite imperfections. But on September 1st, 1983, a Korean Air Boeing 747 strayed into Soviet airspace. Mistaken for a spy plane after ignored warnings, it was shot down, killing all 269 aboard. Investigations revealed the flight deviated over 600 kilometers from its route. The final report concluded the captain failed to activate inertial navigation, mistakenly using magnetic heading instead. You might ask, did they really not notice a 600-kilometer deviation? Did such advanced aircraft lack GPS positioning? Sorry to say, they truly didn't have it back then. Today, GPS is everywhere, from cars to phones and watches. But GPS's development faced major challenges. In Part 3, we explored GPS, 3 simple letters with a complex history. GPS stands for Global Positioning System, specifically the satellite navigation system developed by the U.S. Department of Defense. In the 1950s, when Soviets launched Sputnik, Americans could only listen to its radio signals from the ground. 2 American physicists discovered they could precisely calculate satellite orbits by measuring Doppler shift during Sputnik's passes. That might sound abstract. Let's use a real-world example. If a car honks while speeding toward you, doesn't the horn's pitch change as distance changes? Exactly, that's the Doppler shift. If we can calculate satellite position from ground signals, the reverse should also work. When a satellite transmits its position and precise time via radio signal, ground receivers calculate distance using signal travel time, locating themselves on an Earth surface ring. Theoretically, connecting two satellites narrows your location to 2 points, ring intersections. With 3 or more satellites, you pinpoint your exact position. That's satellite positioning basics. With U.S. Defense Department support, GPS's predecessor, the Transit Program, launched in 1959. But early progress was slow. The first fully operational transit satellite didn't launch until 1964. Initially only for the U.S. Navy, by 1968, 4 satellites were operational, and the U.S. government approved commercial access. However, with so few satellites, ships might wait hours at sea for a positioning signal, and transit only calculated latitude or longitude, not altitude, which might seem unimportant, that the U.S. military needed it to guide intercontinental ballistic missiles for precision strikes. Beyond more satellites, another key solution was the atomic clock. As mentioned, satellite positioning depends on precise signal timing, and Einstein's relativity shows time is relative. For satellites orbiting Earth, their time runs slower than on the ground, about 38 microseconds per day. Compared to traditional timers and quartz clocks, it's impossible to detect such a tiny difference. This naturally leads to significant errors in positioning data, while atomic clocks can measure time down to a billionth of a second, far surpassing their predecessors. Therefore, if we can miniaturize atomic clocks and install them on satellites sent into space, it would greatly boost positioning accuracy. In the 1970s and 80s, multiple satellites with high-precision atomic clocks were launched into space, proving this technology's feasibility. By 1989, satellite positioning errors could be controlled to within 20 meters. Amidst this, in 1973, the U.S. Department of Defense officially merged the Transit Program with another Navy-led time navigation satellite project, forming the GPS system still used today. However, for strategic security, the U.S. limited civilian GPS accuracy back then, so car navigation via GPS was impossible. Thus, businesses hoping to profit from this tech started turning to other positioning systems. For example, Russia's GLONASS system and the EU's Galileo system, which were free, faced competition and U.S. domestic criticism over GPS fees. The U.S. government finally announced in 2000 that civilian GPS would be free, and in 2007 further promised to never differentiate between military and civilian users. Nowadays, with phones and the internet everywhere, GPS-like positioning systems are part of our daily lives. In 2011, 1.6 billion phones were sold worldwide, nearly 40% with GPS capabilities. And in the US, that figure exceeded 90%. Moreover, for more stable location info, many phones can receive signals from different countries' systems simultaneously. GPS gives us just raw numbers: latitude, longitude, altitude, speed, direction. But to make them useful, we need something else crucial: electronic maps. In Part 4, we'll discuss how in the internet age, tech like digital maps and mobile Wi-Fi have changed our travel habits, and what risks come with their conveniences. When talking about digital maps, we have to mention Google. In 2003, one of Google's competitors, Apple, started offering its own navigation service. Facing competitive pressure, Google decided to create its own mapping system. To complete global mapping, Google invested millions and acquired a satellite photography company to capture detailed worldwide photos for map creation. In February 2005, Google Maps officially launched. Users could freely browse any Earth location through zooming and panning. Later, Google invested heavily to update geographic resources, including forming a fleet equipped with GPS devices, cameras, and laser rangefinders. They drove across streets in the US and other countries, generating rich 3D images, now known as Street View. Though Street View offers immersive experiences, its real-world photography has drawn privacy invasion criticisms. Besides streets and scenery, Street View cars capture people's daily activities, vehicles, license plates, and more. Wherever Google Street View launched, from America and Europe to Asia, lawsuits followed closely. Thus, Google made concessions, deleting sensitive photos and developing technology to blur captured faces. However, Street View cars collected far more than photos, including Wi-Fi location data wherever they went. What was Google's purpose in doing this? By adding Wi-Fi data to its map database, Google could roughly locate users in poor GPS areas based on nearby Wi-Fi names and signal strengths detected by phones. In other words, it provided an extra positioning reference beyond GPS. At first glance, this seems reasonable. But after all, today when you open your phone's Wi-Fi menu, you can see nearby Wi-Fi signals and their names. However, beyond collecting public info, Google Street View cars intercepted and recorded Wi-Fi users' transmitted data, browsing history, emails, even online banking info, all captured by Google and stored in their databases. Within just 4 years, this data totaled over 600 gigabytes, equivalent to about 300,000 iPhone photos. Google faced global condemnation. Over a dozen countries investigated it, with governments including the US, South Korea, and Australia ruling it violated privacy and imposing penalties. By May 2010, Google announced its Street View cars would stop capturing Wi-Fi data. Actually, privacy invasions occur not just during mapping. When using maps, we silently betray ourselves too, like when traveling or dining out. And we often pull out phones to take photos, check in, then post on Weibo or WeChat moments. Do you know where check-in history originated? It traces back to a mobile app called Foursquare. Auto-located users while storing millions of venue data, mainly restaurants and bars. To make the app more engaging, developers created the check-in concept. The user with most check-ins at a restaurant became its mayor. They earned a fun cartoon badge and gained rights to review and recommend the venue to others. As users checked in at more places over time, Foursquare realized they could track not just users' real-world movements, but also their economic activities. Thus, they could easily determine spending power. For example, someone checking in at art galleries and upscale restaurants is far more likely to buy luxury brands. Knowing this enables targeted ads. Statistics show in the US and UK, half who received location-based ads visited the store, and 22% made purchases. And more startlingly, among converted customers, 50% had no initial intention to visit. Location is a double-edged sword. When you know where you are, others know where you are too. What we've covered so far involves map surveying by governments or companies like Google. But actually, every ordinary person can create their own maps too. With GIS systems, geographic information systems, creating thematic maps becomes more efficient and solves more problems. Simply put, use standard digital maps as a base, then add your research data to create thematic maps. For example, adding a region's population data, addresses, ages, vehicle ownership, income levels, etc., onto that region's map provides urban planners with valuable references. It helps decide whether to widen roads, add senior care facilities, or plan bus routes. During emergencies, ordinary people can transform into map creators too. This is especially crucial during major natural disasters like earthquakes and tsunamis. When disasters strike, familiar environments can change dramatically in an instant. Existing maps become inaccurate, yet saving lives can't wait. How do we quickly assess disaster zones and launch rescues? During Haiti's 2010 earthquake, a digital map called Ushahidi played a vital role. Volunteers and survivors added post disaster conditions, roads, buildings, to existing maps, quickly compiling updated versions. They also incorporated various incoming information, supply needs, medical aid requests, etc., onto the disaster map. Using this, rescue groups worldwide launched targeted relief operations. Even U.S. Marines assisting admitted Ushahidi's map data was most effective. Sometimes we become surveyors without realizing it. Uh, the perfect example is real-time traffic in phone navigation apps. Green means clear roads, yellow means heavier traffic, and red means congestion. Do you think app makers get this data by partnering with traffic departments? Actually not. The source of this traffic info is none other than phone users. When using map apps, our phones constantly send out our location and speed. Bit by bit, it accumulates, gathering real-time data from millions of users. Map companies can then continuously generate high-precision traffic maps, feeding them back to users for route planning and navigation. From stargazing to street view maps, from compasses to satellite positioning systems, humanity keeps advancing in exploring our world. Today, positioning and navigation tech still has enormous room for development. Meanwhile, protecting personal privacy and preventing tech misuse are equally vital issues. We look forward to these technologies making life better in the future. All right, that concludes our journey through the history of human navigation. Reading notes are below the audio. See you tomorrow.